Well, greetings, mathletes, and welcome back. We're going to be talking about related rates today. Now, related rates is an application of the chain rule, and we don't want to forget implicit differentiation either. It actually uses both of those things, which I suppose technically is still just using the chain rule, since implicit differentiation is an application of the chain rule. But you do have choices because we've covered that already. You have choices on how you want to view these things as we work through them. So in any case, let's go ahead and work through our first example here and see what we got. Okay, so this is an example where we have a line moving along the curve, right? And yes, this is a straight line, but it is called a curve, even though it just has zero curvature. Um, Anyways, it's moving along this curve, y equals 3x plus 5, and it's moving at a constant velocity in such a way that the x-coordinate is increasing by 2 feet per second. And so what we want to know is how fast is the y-coordinate changing? Now, there's some implied things in here. Now, first of all, it's always a good idea to try to get an idea of what this thing looks like. So let's thin that out a little bit. There we go. And then we'll get rid of that and do that again. Right, so this is where to go? There we go, right there. We got a slope of 3, a y-intercept at 5. So this thing's, crossing at 5. It's fairly steep. And basically what we're doing is we're taking a point on this line and we're changing its x-coordinate so that it is moving this way to the right at 2 feet per second. And we want to know how the y-coordinate is changing. So we can see some of this stuff, right? If I change the y-coordinate by 1, or excuse me, the x-coordinate by 1, the y-coordinate's going to go up by 3. And so there's some of that sense in there that you should have a sense that the slope should play something into this. So if we take a look at that equation, y equals 3x plus 5. Okay, now we're talking about a speed here. We're talking about how fast something is moving in feet per second. And you notice we have no variable here that describes time, right? So really what we're looking at, if we're looking for how the y-coordinate is changing with respect to time, we are looking for dy dt. Okay, well, what that means is that we have to take the derivative of all this with respect to t, right? So I need a d dt on this. Well, if I do that, let's see, the left-hand side is going to be dy dt. The right-hand side, I need to take the derivative of, but you have to remember it's with respect to t, not with respect to x. So the derivative of 3x with respect to x would be 3, but we don't know the derivative of x with respect to t right now. And then the derivative of 5 is 0. So this is what we end up with, right? Well, it's telling us that the x-coordinate of the point is increasing at a rate of 2 feet per second, right? That's the change in the x-coordinate with respect to time, which is exactly dx dt, right? So it's telling us that dx dt is 2 feet per second. And so that means that we can take this and just plug it in. So dy dt is equal to 3 times dx dt, and dx dt is 2. Technically 2 feet per second. Well, there we go. 2 feet per second. And so the change in y then has to be 6 feet per second. Right? It's not too bad. Okay. It's actually really straightforward, and this is actually the form of every single problem we're going to look at. You try to figure out what that third variable is you're taking the derivative with respect to, and then you go through and you take it, and then fill in the stuff you know. Right? It's fairly straightforward. Now let's look at the second one here, because you notice it's asking it the question a little bit differently. So we can keep that dy dx is, or dx dt is equal to 2. So I'm going to keep that up there. I'm just going to move this out of the way, and we are going to be changing which curve we're doing. So Now we're looking at this one. Now you notice we're asking for dy dt, which is the same thing it was asking for in the other problem. This time they gave us a point to evaluate it at, right? Which means we're probably going to need to be plugging in more information here. So our curve is this. Y is equal to x squared plus 3x, which is in fact a parabola. If we differentiate this with respect to t, right, if we do a whole ddt on this guy, then we end up with a dy dt. I'm really having to fight myself not writing dy dx for these. There's a place for it, but that's not what we're writing right now. And then here we end up with 2x dx dt. And then the last part would be plus 3 dx dt. Okay, so you notice we actually have this in more than one place here. So let's simplify this a bit. So dy dt, I can factor out that dx dt. It's usually written at the end, but it's still fine this way. Right, so we're looking at this, and you notice we need the x coordinate. Right, there's no place to plug the y coordinate in, so we actually didn't need both of those variables. This could have also been written, find dy dt evaluated at x equals 1, right? That would have been the same problem. But you just see these things in different formats. Okay, so nonetheless, either way, x is 1, which means we're going to be plugging a 1 in here. And dx dt is 2, which means we're going to be plugging a 2 in here. And so that means that dy dt evaluated at the point 1,4 is going to be equal to 2 times 1 plus 3, which is, well, that's 2 times 5, which is 10. Right? And so at that point, it's moving at 10 feet per second. Keep using that whole thing. That looks too much like secant. So we'll just use S. There. That's better. Okay. So that's our introductory example. That's just handling just the mechanics. It's not housed in any kind of a situation or anything. It's just purely algebraic at this point. Okay. So note that we had to use implicit differentiation as we went through this, and we had to plug in values we already knew. So that's what we're going to be looking for is what equations can we set up that we can take derivatives of, and what information can I use to find those derivatives. So let's go ahead and clean this off and look at the next problem here. Okay, so our second example has a little more of a physical presence. We're talking about a spherical balloon, right? And it's being inflated with helium at a rate of 100 pi cubic feet per minute, which is an exorbitant rate. That is super fast. Anyways, what we're talking about here, let's see. Oh, that is not. Let's try that again. All right, we got our little, we have our sphere here, and we have a radius, and the sphere is getting bigger, right? It's moving outward, right? So the volume is changing. And we want to know when that volume is changing, how is this radius changing? How fast is the radius changing? It's actually kind of an interesting question. Well, so what we're going to need is something that relates the volume to the radius, right? We need some kind of an equation that relates the two of them. And conveniently enough, that equation is right here. The volume of a sphere is equal to 4/3 pi r cubed. Right? Interestingly enough, that the surface area of a sphere is actually just the derivative of the volume with respect to r. It's kind of an interesting little thing. You'll notice that with circles too. The area and the perimeter of a circle are derivatives. So in any case, so let's look at what we're given here. So we're given a rate that the volume is changing, right? The volume is increasing at a rate of 100 pi cubic feet per minute. So if that's a DVD, that's dV dt is what that is. So that's 100 pi cubic feet per minute. Well, let's see what we can do. That dV dt, so let's take the derivative of everything with respect to t. That would make this dV dt. Let's see, over here, if I take the derivative of the outside here, that would be 4 pi r squared. And then I need the derivative of the inside, which would be dr dt. And conveniently enough, we want to know what the change in radius with respect to time, and that's dr dt. That's what we're looking for. So let's see here. If we go ahead and plug this in for dV dt, we end up with 100 pi is equal to 4 pi r cubed dr dt. So all we have to do now is solve this for dr dt. So if I go ahead and divide here, let's see, the 4 goes into 125 times. The pi will cancel out. Oh, that should be r squared. I wrote cubed. And then I would divide the r squared over, and that would leave that is equal to dr dt. Now, you'll notice something here. This is a general rate. This tells you how fast it's increasing if you know what the radius already is, right? We have to know the radius here. And so a lot of the time we do get an expression like this. What usually follows it up is after you find the general rate of change, it'll ask you something like, well, what's the change in the rate of the radius when, I don't know, r equals 1, right? The radius is 1 foot. Well, at that point, we just plug this in. And 25 divided by 1 squared is 25 cubic feet, or 25 feet per minute, right? So this, you just think about that. It goes from being 1 foot to being 25 feet in a minute. That's a big balloon that's inflating very, very quickly. But that should give you the idea. So the things you're looking for, especially when you're given a situation instead of just a mathematical setup, you're given a situation setup, is you look for an equation that relates the two quantities, or sometimes there's more than two quantities. But you look for something that relates them together, and then you can take the derivative of that with respect to the other variable. And that's exactly what we did here. We said, okay, we're relating volume to radius. So we found an equation that related volume to radius. And since we're talking about changes over time, I took the derivative of the whole thing with respect to time and plugged in the values I knew. Yeah, and other than that, it's actually pretty straightforward. Well, the devil's in the details. These always give people trouble. So let's go ahead and take a look at the next one then. Okay, so as you can tell, these are going to be increasing in difficulty as we go through this. So just as a synopsis, I'm assuming you've already read this. If you haven't, pause it and read it here. But we have a car moving down a track, and there's a video camera above the track, so it's watching the car go by below. And so the camera has to change angles to keep its focus on the car. And the car is moving at a constant rate. That's basically what we're looking at. So what I always recommend is make sure you read the things that have question marks in your questions, because those are the things you need to answer. So we want the relationship between the change in the angle and the change in horizontal distance of the car. So how far the car has traveled versus what angle the camera is at now. So let's see if we can draw a picture here. So I'm going to start by let's start by turning on my brush. Okay, so we got a camera. Let's just say this camera is, pointed downish. I swear that's a camera. Okay, so we have a straight down angle. Here's our track. Here's our car, right? Vroom, vroom. We'll assume that's a car. And so the camera has to be pointed at the car, right? But the angle is measured from straight down. And so we have a couple of things here. I'm going to go ahead and just call this distance x, since it's what we don't know. We know that this from the problem, this side is 132 feet. Okay, so that's kind of cool. And then this angle right here is measured from vertical down, is theta. Okay, so we have that. Now, what we'd really like to do here is find a relationship between x and theta. And so this should be screaming trig at you. I have a right triangle because this is straight down, right? So this is a right triangle. I know one of the legs of the triangle. I do not know the other leg. I do not know this angle. And so I can set up an equation now. Let's see here. From this angle, it looks like opposite over adjacent would be x over 132. And that would make that the tangent of theta. So this time we actually came up with our own equation that relates the two things. And it's just from drawing the picture that we had to see it. Okay, so we have a relationship between these two. Now, the car, right, this quantity x is a distance. And since we're looking at its velocity, we're talking about the change in distance over time. And we're talking about how fast that theta is changing. And so that means whenever you say how fast, there's always a time component, right? And so that's what you're looking for. So we want the change in theta over time, and we're looking for the change, well, we're looking for the relationship between the change in distance and the change in the angle, right, over time. So what we're going to do is we're going to ddt both sides of this. And let's see here. So that's just a constant. So that would be 1 over 132 dx dt. And the other side over here, let's see, the derivative of tangent is secant squared. So it's secant squared theta. I'll put it in parentheses so we don't get confused here, times d theta dt. Okay, so we need to figure out if we have either of those things now. So dx dt is a velocity, right? It's a change in distance over time. So let's see. Well, we have 180 miles an hour, but that's in miles, and everything else is in feet, right? So let's deal with feet. 264 feet per second is the change in x with respect to time. So this is now 1 over 132 times 264 feet per second. I keep writing that whole, it looks too much like secant. There we go. And that'll be equal to secant squared theta times d theta dt. Okay, if we go ahead and simplify this, I don't know if you noticed, but 264 is 132 times 2, so I can do this, right? And this is just seconds. So really what we're talking about is 2 feet per second. Actually, I'm just going to not bother with the units for the moment. So 2 is equal to secant squared theta, right? D theta dt. I didn't plan this space very well, but that's okay. So if we come up here, if I divide by secant squared, I get 2 over secant squared theta is equal to d theta dt, which is what we're looking for. And just using identities, we can actually make this a lot easier. Secant is 1 over cosine, so that means that we can just flip this around. This is 2 times cosine squared theta is equal to d theta dt. You could work it out the other way also, but I think it's a lot nicer using cosine and sine rather than other trig functions, because you know more of the values for this one. Okay, so we have a function for d theta dt, right? Let's look back at what we were asked again. So what's the relationship between the angle theta, the change in the angle theta, and the change in the horizontal distance? Well, we got that, right? We got no problem here. And then how fast is theta changing when the car is directly below the camera? Well, that's a very good question. Well, if it's directly below the camera, what's the angle? Right? The angle is 0. Cosine of 0 is 1. And so that means that it's changing at 2 radians per second when the car is directly below the camera. Right? It's once you have the relationships, it's just a matter of plugging in values. Okay, so let's kind of just look at what we did again. So we were given our setup, and what we did is we drew a picture that helped us come up with an equation. Because, well, quite honestly, there's not always a formula for these things. You just have to figure it out. Once we had that relationship that related the quantities we want, since we were looking for the changes in those quantities, we took the derivative and then worked from there. So, basically we just plugged in values that we had already found or values that were given to us in the problem after that to finally come down to the answer. These things do take a lot of poking around. It's not uncommon to go down the wrong road first, run into a dead end, have to stop and rethink it and come back and start over. That is completely normal and is completely expected in a calculus course. This is not necessarily obvious material. So, so I think we got that taken care of. Let's go ahead and take a look at the next one. All right, so our last example here. We have a conical reservoir that's draining at a rate of 50 cubic meters per minute. The cone has a height of 6 meters and a radius of 45 meters. If you're not familiar with the word conical, it just means that it's in a cone shape. And so this is a really wide cone. It's 45 meters wide, but it's only 6 meters deep. So we have a big, wide opening. And yeah, this thing's draining. We'll just assume it's draining out the bottom. It's all flowing out here. Oh, that's supposed to be splashes. In any case, all we need is a cone that's draining. There's going to be a height of the water, right? It's going to be at some height anyways. So let's see. Let's just mark in what we know here. So we know that's 6 feet. We know is it all the way across? Let's see. No, it's a radius of 45. So that means it's 90 meters all the way across. We know here we have 45 meters. All right, and then the other thing we're actually given an equation for the volume of a cone in terms of its radius and its height. And since we're given both of those, we actually could compute the total volume of the cone if we wished. What we're looking for is the rate that the height of the cone is changing with respect to time, right? How fast is the height of the water changing with respect to time? So what that means we're looking for is we're looking for dH/dt. Now we have to figure out what we're given. It looks like since the reservoir is draining at a rate of 50 cubic meters per minute, that's a dV/dt. That's the change in volume, right? So we have that. We just need to find a way to relate those things. Well, we have an equation already. So let's take a look at it. So V equals 1/3 pi r squared h. Yeah. So let's see what happens when we take the derivative with respect to time here on both sides. I do want to make a comment about my notation. This is not the proper notation. You really should have each side in parentheses and a ddt on both sides. I'm just shortening the notation a little bit. So that gives me a dV/dt is equal to, let's see here, well, I can pull the 1/3 pi out and just do the derivative inside. because 1/3 pi is just a constant. And the derivative of r squared h, so that's a product, so we're going to use the product rule. 1 d2 plus 2 d1, that would be 2r dr dt. We have a problem here. We're trying to relate dv dt to dh dt. I have a dr dt hanging out in here, so that's a problem. So we have to handle this a little bit different way, because that dr dt is not going to get us anywhere. So we're going to have to start this over and change the original equation a little bit before we can actually get rid of these derivatives. It'd be really nice, or get rid of these derivatives before we can find the derivative. It would be really nice if I could find a way to substitute r out and substitute an h in its place. Well, this is one of those not so obvious things that happens here. You know, if I just look at this right here, in fact, let me switch colors so it stands out. Right? If I just draw this in here, that's a right triangle. And if I draw the water line in here too, that forms a second right triangle. And these two right triangles are similar to each other, right? The height is right here. We don't know what the height is. And the radius that changes, right? Because as it sinks into this cone, the radius of the actual water is going to change. It's going to get smaller. And it's going to keep this relationship between h and r, no matter how small they get, that ratio will still stay the same. So we can set up a proportion here. So before I do that, just to not confuse people, I'm going to get this off of here, and we're going to rewrite the equation of the volume of a cone instead. So looking at this, I can say that h over r, let's see, that's that. Well, we know the total height is 6, and the total radius is 45. So we actually have a little proportion we can use here. And in fact, I can simplify that down to 3/15. And so h is equal to 3/15 r, or r, which is actually the better one for us to solve for here. Let's see here. Let's go ahead and swap that around. Is going to be, let's see. Oops, I said it backwards. R is going to be equal to 15h over 3, right? Just solving that proportion, just cross multiplying and simplifying. Well, what that means is we can take this value and plug it in for r now. So that means we're changing this to v equals 1/3 pi times, well, r is 15/3 of h, so that means we're going to be multiplying 15/3, oops, don't want to close it yet, 15/3 h squared times h, right? Because this is r. So what I just did is I just found a way to substitute out the r, so I have all h's. Okay, so I'm going to switch colors so this stands out a little bit better. So this is what we're going to be dealing with. Try it one more time. I was trying to underline that, but I had the eraser on. Okay, so this is what we're going to be dealing with here. Let's go ahead and simplify this up. So v is equal to, let's see, if I square all this stuff, that's going to be 225 over 27 h to the third. Right? That's not so bad. I don't think I missed anything in there. Okay, so we have this now. Excuse me. Actually, I think we can simplify that down. Let's see what we can do with that. Let's see, 3, no, there should be a 3 in there. So it should be 75 over 9 or 25 over 3. Okay, so we can go down to 25 over 3. Okay. Now we can take, now we can go ahead and do our dv dt. We'll do our ddt of both sides. So dv dt is going to be equal to, let's see here, we pull that 3 down in front, that gives me 25h squared dh dt. That's better, right? Now, we know already that the volume changes at 50 meters cubed, but we have to be careful here. Since it's draining, it's negative 50. So I end up with negative 50 is equal to 25h squared dh dt. And if I go ahead and simplify that, I'm running out of room real fast here. Let's see, that gives me negative 2 over h squared is equal to dh dt, right? So it's proportional to the inverse of it's proportional to the, I guess it's an inverse proportion to the square of the height, basically, is what this says. Now, if we want to know how fast the height is changing at any point, right? Plugging in the actual height will give us something negative, which means that the height is going down. So that makes total sense. So for part B, if I plug in 1, right, it's changing at negative 2 feet per minute, or meters per minute. If I plug in, what do you call it? If I plug in 2, then it's 1/2 of a meter per minute. And this makes sense, right? If you think about this thing dropping, it has a lot less volume to get rid of at the bottom, so it's going to be moving faster. The shorter the height gets, the faster it's going to move. Cones are really interesting. It's one of those things I always find it fascinating to find like the halfway point of the volume on a cone, because it's not where you would expect it to be. So that's actually a fun little exercise that you can do sometime. But nonetheless, notice that this one was different because we had to substitute out one of the variables first. And that's actually a huge challenge most of the time, to figure out how to reduce it down to just what you need. So let's see here. There it is. All right, so that concludes what we were supposed to talk about today. And so until next time, keep your pencils and your wits sharp.